Section 10.2, Shapes of Molecules and Ions, VSEPR Theory. Go and watch video problem 52 after this for some examples. Now, this is a pretty important section. Right? It's used in explanations a lot. And what you have to keep in mind is this idea of electron domains that we described in the last section. Okay, so make sure you look at that idea of electron domains. And we're going to use that extensively here. Okay, so we looked at Lewis structures. Now what we're looking at is the actual three-dimensional shape of the molecule or ion. And that three-dimensional shape is determined by what they call the VSEPR theory, which that is the valence shell, which is the outside shell, electron pair repulsion. So in other words, what we're saying is that the outside electrons, they will repel each other, right? So here, take a look at with CO2. Now, again, we're looking at electron domains, okay? So if we have two electron domains, the atoms want to get as far away from each other as they can in order to minimize that repulsion. So as far away as they can get is 180 degrees. So anything that has only two electron domains is always going to be 180 degrees away from each other. Now, we call this electron domain geometry linear. Okay? So we're going to be talking about electron domain geometry, which is how many electron domains are on the atom or on the molecule. And we'll also be talking about what's called molecular geometry or molecular shape. And they're two different things. Okay? So, two electron domains, it can be linear. That's it. That's it. All right? Now, if there are three electron domains, in other words, there are three sets of electrons that are surrounding that central atom, or three areas, I shouldn't say three sets of electrons, strike that, three areas that are being occupied around that central atom. So, for instance, right here, right, CH2O, we have 1, 2, 3 areas being occupied. So that's 3 electron domains. Now, this is going to be 120 degrees away because that's as far as it can get without getting closer. Alright? So all those atoms are 120 degrees away from each other. And when it's just atoms, then we call the shape trigonal planar. So that would be the electron domain geometry. That would also be the molecular geometry. Right? Now, if we have lone pair electrons on that central atom, the molecular geometry changes. Okay? So if it's only atoms, the electron domain geometry and the molecular geometry will be the same. If it has lone pair electrons, the molecular geometry will change, and I'll show you that here. So here, let's again count up how many electron domains. 1, right? So that's 1, 2, 3 electron domains. Okay? So since it has 3 electron domains, the electron domain geometry is trigonal planar. But the molecular shape only looks at the atoms. So we no longer care about those. Alright? So the molecular shape is bent, or it's also called V-shaped. Now let me show you how to draw these real quick. For the linear, it's pretty simple. It just looks like this. That's how we draw it. For the trigonal planar, just as you see it there, looks like that. Now once we start to get lone pair electrons, we do something slightly different. So here's your sulfur. Right? Here's your oxygen atom. Here's your oxygen atom. Now we draw a balloon and we put a couple dots in there. Okay, and those are the lone pairs. So those are the lone pair electrons. Okay? Let's move on to 4 electron domains. Okay, so here's methane, CH4, 1, 2, 3, 4 electron domains. They're all atoms, so we call that tetrahedral. So the electron domain geometry is tetrahedral. Now we start to introduce this wedge and dash model. Okay, so here's carbon, hydrogen, hydrogen. So those two hydrogens and carbon they're all in the same plane, so we just draw them like that. Now this hydrogen is actually sticking out of the plane. Right? So that hydrogen's coming at you, and then this hydrogen is going into the screen. Okay, remember this is a three-dimensional structure. So this shape, this angle, ends up being about 109 degrees, 109.5 degrees, depends on the size of the atoms. Okay? Now let's come back up here real quick, because I mentioned that this was 120. This is actually less than 120. And the reason why it's less than 120 is because now we have these lone pair electrons on here, and those lone pair electrons are actually pushing or repelling those bonded atoms greater than this atom would, okay, which ends up pushing it closer than 120 degrees. We'll see that down here. So let's go back to 4 electron domains. So there's 4 electron domains. It's tetrahedral. Here's 4 electron domains. Here's 4 electron domains. So we got, give me that, 1, 2, 3, 4 electron domains. So that means that the electron domain geometry is tetrahedral. Okay? But the molecular geometry is what's called trigonal pyramid, because it's a three-sided pyramid. Can you see that three-sided pyramid there? There's one side, there's the second side, and then the back side is the third side. So that's a three-sided pyramid. So that's why it's called trigonal pyramid or trigonal pyramidal. To draw this, we're going to draw central atom. Remember, lone pair electrons go in a balloon. Okay, now the lone pair electrons in this atom are in the same plane. We've got a wedge, which is coming out at you. We've got a dash, which is going back into the screen. Okay? And again, that's trigonal pyramid. Now, this angle right here, remember this angle up here was 109 degrees. This angle is going to be less than 109 degrees. Okay? Because again, these lone pair electrons are pushing on these atoms with greater repulsion, which makes them get closer to each other than they normally would be. Alright, the final electron domain geometry for 4 electron domains. Let's see, we got 1, 2, 3, 4. So there's 4 electron domains. That means the electron domain geometry is tetrahedral. Right. But if we're going to describe the molecule, take a look. It's bent or V-shaped. So we've seen this before. Okay, let's go ahead and draw this one. So here's the oxygen. Let's go ahead and color it red. Oxygen's usually red when you're working with molecular models. Here's a balloon. That's lone pair electrons. Lone pair electrons down here. And then we've got the wedge coming out at you. And we've got the dash going into the board. Okay, and again, that's bent or V-shaped. Okay. So you can have, we only go up to 4 electron domains. In AP, we cover the 5th and the 6th electron domain geometries. But for 2 electron domains, just to summarize here, you are linear. 3 electron domains, you are trigonal planar. 4 electron domains, you are tetrahedral. Okay, and then what happens if you have lone pair electrons? So these, all of these, are no lone pair electrons. Right? One set of lone pair electrons, LPs I'll call them. Well, you can't have that in linear. You could, but it's just still going to be linear. Trigonal planar, it now becomes bent. And tetrahedral now becomes trigonal pyramid. What if you have 2 sets of lone pair electrons? It's not going to happen in linear. It's not going to happen in bent or in trigonal planar. For tetrahedral, then it becomes bent. Okay? So here, table 10.3 summarizes it fairly well. Same ideas, right? Same ideas. if we look at these bond angles, I would actually change some of these. So I would say that this one is less than 120, this one is less than 109, and this one is less than 109. So it's, you know, it gets even smaller than the one prior to it, right? So if this is 109, this is less than 109 because it's being pushed closer with those lone pairs. This one is going to be less than 109 because it's being pushed even greater. All right? So go and check out the sample, the video problem, and you'll be in great shape. See you at the next video.